Welcome to Stereochemistry at Vedial Vegapare. In this video, we will see an introduction to enantiomers, RS notations, DL notations, and plus and minus notations used in stereochemistry. So let's see some of the basics of the enantiomers. We all know every object has a mirror image. So if the mirror image is superimposable, then the molecule and its mirror image are said to be identical. Say for example, a conical flask. In this conical flask, we see the mirror image and the original molecule have a superimposed structure. And because they superimpose on one another, the molecule is said to be identical. Or in other words, the vessel is said to be identical. Similarly, we can also talk about non-superimposable mirror images. A non-superimposable mirror image is one where the molecule and its mirror image do not match, like the example of our right hand and a left hand. So the right hand is the mirror image of the left hand, and we see that when we keep the two hands one over the other, they do not match. This is the reason why we cannot use a left hand glove on the right hand or the right hand glove on the left hand. We can extrapolate this to that of organic molecules. Now, how do I find that this difference in organic molecules? So, an organic molecule will also have its mirror image. So, how do I find out if the mirror image is superimposable or non-superimposable? And accordingly, I can go ahead and define the term enantiomer. So if the mirror image is superimposable, then the molecule and its mirror image are identical. They are one and the same molecule. Whereas if the mirror image and the molecule are different, then they are two different molecules. So by definition, enantiomers are stereoisomers that are mirror image isomers and are non-superimposable. So we will see in the later videos, about how to look at molecules and how to see whether they are non-superimposable. Now we will see certain basic criterion for a molecule to be an enantiomer. The first and foremost thing is it is a mirror image. So they are mirror images of each other. They are not different molecules, but it is a molecule and its mirror image. And secondly, all enantiomers will rotate the plane polarized light in the opposite direction. Suppose if the original molecule rotates the light to the right, the other one rotates the light to the left. And one of the fundamental criterion for a molecule to be an enantiomer is chirality, or it must have at least one chiral center. So we know pretty well a carbon that has 4 different groups attached to it is called as a chiral carbon. So in this image you see the center black color is the carbon, and there are 4 different groups, different colors used to designate. There are 4 different groups surrounding the carbon. So this molecule and its mirror image are non-superimposable and they are enantiomers. A very good or classical or example is lactic acid. We know lactic acid is present in milk. It is also present in the muscles when you have when you do exercises. It is secreted or released in the muscles. So lactic acid is also a molecule which is having a chiral carbon. So this is a Fischer's notation, wherein the point of intersection of the lines is a carbon, and then there are 4 groups attached to the carbon atom. Similarly, on the other hand, this side, the D-lactic acid, also has the same set of groups but as mirror images. So we see here in lactic acid the molecule and its mirror image. It could be either way. It could be L or D, plus or minus. So coming to naming conventions, there are 2 things that we have to remember. One is optical rotation, another one is configuration. So optical rotation is how the enantiomer behaves experimentally. So when I put this lactic acid in a polarimeter and observe its angle of rotation, I will know that it rotates the plane polarized light in the right direction and it is plus. Similarly, how do I write the structure of this enantiomer on paper? So if I say plus lactic acid, writing its structure may not be feasible. So in order to facilitate writing of enantiomeric structures, configurations were assigned. So these configurations were useful to actually write the structure of enantiomers on paper. So in this example, what we have seen here, L and D are configurations. So now let's take up optical rotation first. So it is an experimental value and we all know all enantiomers are optically active because we know that they have the ability to rotate the plane polarized light. And because they have the ability to rotate the plane polarized light and are optically active, they are also called as optical isomers. Each enantiomer had a characteristic angle of rotation and it is called as specific rotation. So all optical isomers are given the notation plus or minus based on the direction of rotation of the plane polarized light. So in lactic acid we see plus lactic acid rotates the plane polarized light to plus 3.7 degree, whereas minus lactic acid will rotate the light in the negative direction, which is minus 3.7 degree. So moving over to configuration, wherein we use the notations D and L. So this notation D and L is popularly used in carbohydrate and amino acid chemistries. Emil Fischer was a person who first proposed this notation. This is to help in the easy drawing of structures of carbohydrates and amino acids. The notation D is used by seeing the structure of the organic molecule, writing it in the Fischer form, and when the first OH group from bottom is written on the right hand side, then the notation D is given. And when the OH is written on the left hand side, the notation L is given. So let us see the structure of lactic acid. Again, in lactic acid, you see from the methyl, the first carbon at first group at the bottom is methyl, and so the carbon which comes from bottom, the first carbon has the OH group. So the position of this OH group helps us to write the structure of the molecule. So in this case, lactic acid is given the notation L because the OH is on the left. Similarly, on the other side, you see the OH is on the right, and so the lactic acid is given the prefix D. So the D and L were written with respect to OH group's direction when we write the structure of the molecule. But later, configuration was better written using RS nomenclature or RS notation. So this notation was proposed by Can, Ingold and Prelog. And what we have to remember in this notation is all S is not L or plus or vice versa. In the sense, if a molecule has a prefix L and plus, it doesn't mean every molecule will be Ln plus, or if it is L, it must be S. It is not like that. So all molecules will have different configurations and different optical rotations. Like we see in the case of lactic acid, we see the S isomer and the R isomers, which are D and L respectively. So the next video we will see how to assign RS notation. Thank you.